workable for that. Consider possibilities, consider alternatives, consider what the positives and the negatives are in each. This is doing systems. People will invent all sorts of new things. People will decide this matters and this doesn't matter for my workload or for my customers. There's a huge amount of attention people pay to what customers care about. And I will again remind you of the tragedy of working on optimization. You improve things for 99% of the people, or leave it as was, you'll hear from the 1%. Okay, so you can combine the two approaches. What you could do is you could go ahead and keep track of something where you keep histograms and you say, here are my 10 most common values, here are my 10 least common values. Because those are the ones that will mess up your calculations the most, particularly the high ones, but the low ones too sometimes. So you're going to say, here are my 20 values that appear most often. I'll keep track of what the exact percentage is for those, the exact reduction factor is for those. And I might do it for the low ones as well. And so basically, what you might even do, and this relates to the question that you just asked, is I can bucket my buckets. So remember, inside my buckets, I'm using uniformity assumptions. It might be that in cases, I would choose for certain buckets where within the bucket it's not really uniform. I might go, recursively bucketing within a bucket, only for the buckets where it matters. So there are all kinds of things that you might go ahead and do for playing the ranges. And I've already emphasized this, but there are things that mess you up. You have a query and you say, I'm going to optimize this query. Well, actually, I'll throw this out with you. We've talked about several different possibilities. I have a query where it's a parameter. I'm looking for students, and a complicated query where state equals $X. $X might be California, it might be Kentucky, all the rest of it. One of the things I can do is just optimize that query independent of what the value of X is. Great, I've got a plan, I just use that plan all the time. The trouble is that a plan that's really good for California might be terrible for Kentucky. No offense to Kentucky or California. So what might I do about that? Anybody want to talk about possibilities? I mean, one plan to rule them all could end up working. What are alternatives? I could optimize the query independently every time I get a value. But, well, there are only 50 states, but if it's something where salary is in a range or something like that, and it's parameterized, there are a whole bunch of different queries to keep track of. Or what I might try to do is to figure out about the high frequency states and the low frequency states, play histogram games with respect to the parameters. There are all sorts of different approaches that can be taken to this that end up being exciting. Also, we're not going to spend time on this. The amount of buffers, the amount of memory, and other resources that I can throw at a query affects how good the plan is. Remember, we've talked about assuming that there's a given number of pages available to optimize the query. It can really have a big effect. It has a big effect on sorting. It has a big effect on join algorithms. If I'm in a situation in which I have a wealth of resources available to me, and today that's much more common than it used to be, and I have a whole bunch of different queries, then everything runs nicely because I can throw a huge amount of CPU and memory and networking at solving the problem. But I could have something in which I'm poor. That happens. I don't have as much resources and I need to get the query done. The plan that's better in that case may end up being different than the plan that's better when I'm resource rich. And again, optimization, the problems are way beyond what we're talking about in this class. And there are decent solutions here. Now let's look at nesting. Okay, so here is a query up there. So we're going to select the sailor names where there exists something where inside reserves where the boat ID is 1 of 3 and that sailor is the one who reserved the boat. Now I can't transform that into well, I might be able to transform that into a join. In fact, the join equivalent is shown below. Well, what I'm doing is I'm only getting I do select sailor name, but it could be that there are several sailors who have the same name. So in this case, what I'm saying is I'm getting rid of the duplicates, even if there happens to be 2 sailors who have the same name. But basically, that's why the distinct is up there. But the thing that's written below doesn't involve nesting, and it involves doing a join instead. And in this case, it happens to be completely equivalent. If I'd written the top one without a distinct, they would not be equivalent. Because I don't want to get rid of duplicates if there happen to be two sailors who have the same name. The thing is that with the join, I will get a match for every time that sailor reserved boat 103. So if John Smith reserved 103 12 times, if I don't have distinct in the bottom query, I'll get 12 matches for John Smith if I didn't have the distinct. But since I have the distinct, those two queries happen to be equivalent. So, I mean, the nice thing about writing it with the join is that I don't necessarily have to start with the sailors relation. If I'm following the really semi-procedural way that's shown in the top query, I go through all the different sailors and I see whether or not there is a reserves of boat ID 103 that corresponds to that sailor. But if I do the thing below, I could start off with the reserves and start off with all the reservations of boat 103. Would that be better or would that be worse? It depends. Depends on the statistics. So for each reservation of boat 103, I can go ahead and I can get the sailor ID that corresponds to it. Okay, so that would end up working. And frankly, the only reason that I have to go to the sailors table is that there might be reserves where there isn't referential integrity, where there's no sailor corresponding inside the sailors table. But anyway, those things are equivalent. So bottom line is, the bottom line on this is that if I'm doing it using the nested way, I have to optimize each query block. So basically, I have to be able to go through the sailors, and once I have, again, my hand around that neck of that poor sailor, too much violence in database. Once I have a tuple from sailors that I'm working with, I have a fixed value. And so what I'm optimizing is a subquery select, where exists, select from reserves where the boat ID is 103, and the r.sid is that fixed tuple. So for example, if I have an index on the SID column of reserves, which could be a B tree or it could be hash, then I have that particular value of the sailor's SID in my hand. So if I have that index on SID, I could look that up. If I have an index on BID, I could look at the reserve tuples based on that. If I have both, I can do index intersection. So again, the outer block is optimized with the cost of having to call the nested block included. I have to figure out about the cost of executing the inner block, and that affects the cost of executing the entire outer block, because the outer block only works based on finding what's going on, whether there actually exists something that ends up matching. So basically, by saying procedurally, and again, SQL looks procedural the way this thing is written. I grab a sailor and then I see whether there exists a reserve. If I transform it into that thing that's on the bottom, that's part of what an optimizer does. It tries to find different ways of executing the query, some of which may be less procedural, where it can give the same answer, and it optimizes multiple different things. I have to tell you, there can be 20 different rewrites that you can have for a query that get considered. And some of them, not necessarily all, get optimized, cost optimized, and then you fix the best plan. So remember that optimization consists of this basically translation into a different form. The query rewrite part of the optimizer finds other equivalent ways of writing the query. And then multiple of these things, not necessarily all of them. You may use heuristics to limit which ones to think about. Because again, you get an 8-way query, there are too many different things to think about. So you have heuristics about which rewrites to consider, as well as how you do the optimization of the 8-way join. But in this particular case, the nested version of the query typically ends up being optimized better, because you can try, basically you have the equivalent of every one of the semi-procedural plans that you have up there, plus you can also consider where reserves gets access first. So again, query rewrite is again a very complicated thing. And we're not going to go through it, but you'd be amazed, and there have been some papers written on this, you'd be amazed about all the optimizations that can be done with respect to group by. translation of course, group by and having and where and project and all of the translations that can exist there. Interesting field. So to finish up optimization, and I will barely get started on transactions, which is my next topic. Query optimization is an incredibly complicated and difficult stuff. You again have this wonderful declarative, at least close to declarative property on SQL. Somebody's got to pay the price for it. The people who work on the optimizer, on the rewrite and the costing, pay the price for it. There's a lot more that gets done than what I've described here, especially in modern optimizers, including learning, including keeping a lot more statistics, including trying multiple different plans and seeing which one actually ends up being better. I mean, there are systems that may lie fallow at certain times where not a whole lot of work is going on, or you choose to, let's say you're running in a cloud, you choose to pay some extra resource just to do some extra experimentation, where you're not slowing down somebody's execution to do it, but you're doing an extra experiment to see what the result would be had I done it in this other way. So, optimization affects database design. The choice of which indexes you have. I mentioned this in 180, but I'll emphasize it here. There can be a fixed set of access paths, indexes, hash, many other things that you have that you use. And then you want to pick the best based on what exists. But there can be cases where something is so darn slow if you don't have a certain access path, where it's worthwhile to construct that access path for executing the query. And maybe you keep it around and maintain it, and maybe you throw it away after you executed it. That's a plan. That's a plan which is perfectly legitimate. Create this index, but don't bother maintaining it in the future. All sorts of different choices made. There are more plans than you would think, because you have all these other choices. So figuring out the best way of executing a workload, you keep a set of things around. There are things that you may create and throw away. Optimization, rewrite, cost optimization, have to prune the space to be able to do it. You estimate both the cost and the size of the result, because sizes affect the result. The size, again, no matter how you get ABC, you're going to keep, remember, you're going to keep the cheapest uninteresting plan for getting ABC, because you're going to be joining it with DEF later as you go. You keep the cheapest uninteresting plan. You'll also keep interesting plans. What's an interesting plan? Well, you do a little bit of extra work. It might be more expensive, but it'll save you some work later. E.g., because you're going to do a merge join, and if you get ABC already sorted on the column you're going to need for the merge join, it'll save you doing the sort later. Same thing with respect to help with group by and order by and other things. We talked about that. You will keep the cheapest uninteresting plan. You will keep the interesting plans, or at least a bunch of them. And if the cheapest plan is interesting, there's no need to keep an uninteresting plan. By the way, I think I told you this. You know the proof that there are no uninteresting numbers? I think I mentioned it. I'll just mention it again very quickly. If there were uninteresting positive integers, take the smallest one. That's interesting. So there are no uninteresting positive integers. Anyway, but there are things that are uninteresting, meaning that it doesn't help you later. So you keep the cheapest uninteresting one, and you keep interesting plans, but if the cheapest interesting plan is cheaper than all the uninteresting, you don't bother keeping the uninteresting one too. So again, there's the issue about what statistics do you keep, how do you keep them up to date, what indexes do you have, what do you store in the catalog, what do you store in memory? There are all these different implementations. Chicken and egg problems. Which join methods do I have? Which optimization techniques do I use? How do I pick the best plan? What if I have a plan that's pretty good all the time versus another plan that's sometimes very good and sometimes terrible? Which one do I pick? I'll give you two answers. One of them is pick the one that's pretty good all the time. Another answer is have a case statement where if you can figure out whether or not you're in the places where the good plan is really good, not bad, take that gooder plan, that better plan, for those cases. But for the cases where it's not so good, pick the one that's pretty good, because basically take the envelope of keep a bunch of different plans. And if you can separate, I've got 4 plans. Here's my space. In this case, this one's good. In this case, that one's good. In this case, I don't know which one of these is better, but sometimes they're really terrible. So maybe I'll pick one of the other two because the goal is to avoid terrible. you know, and I can't figure out whether it's terrible or all kinds of strange considerations go into this stuff. It is better to avoid surprises than to sometimes be wonderful and sometimes be terrible. People set expectations about what the performance is going to be, and if you suddenly violate those expectations, somebody's going to get unhappy. Running in 200 to 300 milliseconds, let's say, all the time, which is about what people can notice as time, it's much better than sometimes running in 100 milliseconds and sometimes running in 600 milliseconds. Okay, we saw how to deal with single relation queries. You consider all the access paths, pick the cheapest for each different table. Any table could be the first one that you access, not necessarily, you know, fixed order. And you want to have things where, well, you can always scan, and sometimes that's a good idea, but sometimes you can do better by taking advantage of an index to be able to access the thing. I will also, again, remind you just briefly about NUMA. It might be that there's data that you are keeping inside memory that you're using. If the index pages are not in memory and you have to wait for the index to be run, and that can end up being expensive. You can end up needing a lot more memory to keep a lot of more stuff on the index. So again, scans these days end up being more serious than they used to be. When you have a multi-relation query, you say, okay, I've got the, you know, the 7-way join that I'm doing. I'll figure out the best way of getting each table as a first table, then the best way of adding each table to it, not doing Cartesian products unless necessary, right? And so I'll just see about retaining the cheapest plan, but again, I will be keeping, my size will be estimated in a way that's independent of how I got it, whether it's ABC, CAB, BCA, BAC, or any of the 6 possibilities. And then I'll keep going until I've joined in all the different relations, and I'll keep the cheapest plan overall. At the end, there's no such thing as interesting. There's just whatever plan I have for executing the entire query, because there are no more steps to consider. When I've got all 7 tables joined together, I've got my results. But I will keep interesting orders as I go through, because those, again, may pay a little extra, save a lot of money later. Could be. Okay? And just as pointers, again, it's a paper I mentioned already. Goetz wrote a paper he got his PhD at Wisconsin. He worked at a number of places, Microsoft and HP, and he's currently at Google. Again, it's a great survey of query evaluation techniques. Guy Lohman, who recently retired like a year or two ago from IBM, wrote a Sigma blog post. It's query processing a solved problem, and he has a whole bunch of interesting papers in his bibliography. The answer, hell no. Remember, as hardware changes, as you know, GPUs, non-volatile memory, as there more memory to be able to keep track of things, more experiments going on with lots of cores, it'll never be a fully solved problem. There was a problem, a paper having to, one of the earliest papers 10 years ago, having to do with machine learning and using that for optimization. That was out there. And how many of you have heard of Spark? I wish it was more. So Google did MapReduce, which, as we talked about, is a lot like aggregation group up, but for big data. Yahoo then created Hadoop, which was open source. And again, open source ways of dealing with big data. About 7 years ago, a project called the Amp Lab at Berkeley created something that was called Spark, which is, again, another way of playing with doing MapReduce with a different technique for how you handle recovery, which, again, I'm not going to have full chance to go over in this course, but it is worth learning about Spark. And just to show you that even when you have no SQL, that everybody still cares about SQL, they did a project called Catalyst, because people take courses like this, they learn SQL. You want to be able to take advantage of SQL to be able to do complicated queries even on big data and to be able to optimize them. So they had a system called Catalyst that was described in SIGMAT's 2015. Again, it keeps evolving. That deals with how you optimize on top of the Spark, which again is a variation, much improved in performance compared to Hadoop for a range of different reasons. I've posted, but I didn't think I'd necessarily get much into it. There were going to be 3 lectures that we do talking about transactions. The first one of those has been posted. We will start on that on Wednesday. If there's anybody who did not get the midterm on Friday. I have the midterms here, so you can pick them up for me. I don't have your cheat sheets, I'll have to bring those in another time, but I do have the midterms if you want to pick them up. And as I mentioned, I expect Project 2 grades to be posted today, but then I thought they would be over the weekend, but there's still some discussion going on one or two points. So anybody want the